In the eyes of quantum field theory, the vacuum isn't empty. It's alive, seething with energy, fluctuations, and possibilities. What we often imagine as nothingness is actually a churning foam of virtual particles popping in and out of existence. And among these virtual specters may hide the most elusive and controversial of all: tachyons. The quantum vacuum is not calm. Even in the absence of matter, it contains the potential for everything, a background hum of probability and uncertainty. According to modern physics, particles are simply vibrations in quantum fields. The electron, for example, is a ripple in the electron field. Photons are ripples in the electromagnetic field. So, what happens when a quantum field becomes unstable? It tries to find a more stable configuration. This process is known as spontaneous symmetry breaking, and it's often accompanied by strange signals in the math. One such signal is a negative squared mass, the defining feature of a tachyon. This doesn't mean the particle is literally imaginary. It means the vacuum state is unstable, like a marble sitting atop a hill, ready to roll into a valley. That roll is called tachyon condensation, and it's how fields find stability. In the 1970s, when string theory was being developed, physicists found that some string models naturally predicted tachyons. At first, this was seen as a flaw, a bug in the theory. But over time, researchers realized that tachyons could signal a transition from one vacuum state to another. This is similar to how water vapor condenses into droplets, a phase shift. The presence of tachyons, then, wasn't a problem. It was a clue to how universes might evolve. One of the most famous places where this idea comes into play is in bosonic string theory. This early version of string theory had a tachyon in its spectrum, which led scientists to explore whether this indicated an instability in the space-time it described. It turned out that once the tachyon condensed, the system rolled into a more stable vacuum, and new possibilities emerged. In this context, tachyons are not travelers. They're triggers. They don't necessarily exist as particles zipping around faster than light. Instead, they exist as signals in the equations, indicators that a transformation is about to happen. But that doesn't make them any less mysterious. If tachyons are connected to vacuum instability, could they be tied to the early moments of the universe? Some theorists believe that the very birth of our universe, the moment of cosmic inflation, might have involved tachyonic processes. The vacuum, unstable and super-energized, exploded outward, expanding faster than light itself. In fact, inflation theory requires fields with negative pressure, a key feature of tachyonic behavior. And perhaps, as the universe expanded and cooled, tachyon fields settled, locking in the laws of physics we know today. But what if some of those fields never fully stabilized? What if remnants of tachyonic energy still lurk in the structure of space-time? Could they be driving dark energy, the mysterious force accelerating the expansion of the universe? Some models suggest that tachyon fields could provide a candidate for dark energy, a slow-roll field whose energy never quite dissipates. This would mean the fate of the universe is still being influenced by a field born in chaos, a ghost of instability, guiding galaxies ever farther apart. But there's another possibility, that tachyons appear not just in cosmic beginnings, but in black holes. The region near a black hole's event horizon is a cauldron of warped space-time. Some physicists speculate that under such extreme conditions, vacuum states might again become unstable, and tachyonic fields could emerge. If this is true, then black holes could be gateways not just to destruction, but to transition, points where space-time itself reconfigures, where new universes could be born. This ties into the idea of cosmic censorship and the information paradox. If tachyons exist near singularities, they might play a role in information conservation or in spawning baby universes. But even if these ideas remain speculative, They offer a tantalizing glimpse into the deep fabric of reality. Tachyons, in this sense, are not merely fringe physics. They are mathematical beacons, guiding us through the fog of quantum uncertainty toward a more complete theory of everything. A reminder that the vacuum, that supposed emptiness between stars, is anything but empty. Instead, it may be the most dynamic and creative realm of all. So, the next time you stare into space and think you're seeing nothing, remember, you're looking at the birthplace of possibility. And somewhere in that quantum sea, the ghost of a tachyon may still be dancing.